Okay, let's take a look at this video. The question is, what's inside a wind turbine?
A typical wind turbine generator, as found on wind farms across the world. Now, exact designs do vary, but almost all the turbines in use today are horizontal axis machines, which have a 3-bladed rotor spinning in a vertical plane attached to the front of a box, which we call the nacelle, after the fairing around an aircraft engine. And in this nacelle, we have the generator, often a gearbox, and occasionally a high-voltage transformer, and the whole thing sits on top of a tower, which is mostly there to keep the blades from digging a hole. We tend to class turbines by their power output, hence their physical size. Wind farms might use many sub-megawatt turbines, each producing 400, 600 kilowatts each, or a few multi-megawatt turbines producing maybe up to 3 megawatts per unit. Apart from physical scale, they are arranged a bit differently. So let's start by looking at a typical sub-megawatt model. Turbines of this type are typically 25 to 45 meters tall, and at the base you will often find 2 doors. The lower door takes you into a secured compartment where we have a high voltage step-up transformer. The generator at the top of the turbine is producing about 690 volts, and this transformer converts that into several thousand volts to send it more efficiently to the substation. The main entrance to the turbine is at first floor level, and there we find the control cabinet and the base of a ladder, or a series of ladders. Often in these smaller turbines, the ladders run to a series of platforms and they change sides at each platform to give you a rest area and a bit of fall protection. Platforms are generally just wooden discs suspended inside the tower walls, and they might have a trapdoor or a set of guardrails and a gate, depending on how the ladders are arranged. The main run of cables goes up the wall of the tower, dodging past any intermediate junctions, because obviously the towers can't be delivered in a single 40-meter long section. They come in 20-meter long sections that bolted together with a lot of nuts and bolts. But as we move higher and higher through the platforms, they're getting slowly narrower and narrower, so the ladders are getting a little bit closer together. But eventually, the main cables stop being attached to the wall, and they hang freely in the center of the tower, so they can twist as the nacelle rotates to face the wind. If they twist too many times, the nacelle will spin itself around to remove the twists. But as we move up, now the cable goes through a hole in the center of each platform, and at the top of the tower we have a steel platform with a sealed trapdoor, which we call the yaw platform. Just above that we have the yaw ring with the bearings that allow the nacelle and the rotors to rotate around to face the wind. And this sealed platform acts as a bit of fire protection, also avoids people falling back down the tower, because at the top of the nacelle we simply have a hole which we climb. And the nacelle in this case is a spagely tapered tube. At the back we have the wind sensors, which give us speed and direction and allow the turbine to face into the wind and to change the angle of the blades. The nacelle itself is just a fiberglass tube. At the front we have a similar fiberglass cowl protecting the hub, which is a steel casting on which we have bolted on 3 blades. And the blades can turn or pitch so that the angle they form with the wind can be varied. Out at the back of the hub we have a shaft which leads into the gearbox, then a high-speed shaft through a brake into a generator, and that generator then supplies the electrical power, as I say, at about 690 volts all the way back down the tower to the base. And right at the back we have a cooling fan, as we're generating 500,000 watts of energy inside the nacelle. Some of that is wasted as heat, and without an efficient cooling system there is the potential for the turbine to catch fire. Now, the layout of a larger turbine is broadly similar, but some of the components are in different places. So let's start by looking at the tower section of a typical 2 megawatt turbine. Where we place the high voltage transformers in multi-megawatt turbines is a lot more variable. Quite frankly, we have a lot more room, so we can decide if they can be in the nacelle, they can be at the base of the tower, they can be on platform 1 in the basement, they can be outside in a hood. In this example, the transformer's at the top, so when we go into our door, the one thing we will not find is a transformer. We do have the high voltage switches, in this case on platform 2, but on the entrance platform we have the usual control cabinet and a lift, a little green box. And that lift will take 2 people to the top of the tower, or nearly to the top, without them having to climb the single, very, very long ladder. Almost all large turbines will just have a single run of ladder for the majority of the run of the tower. It will have a wire or a rail system, fall arrest device fitted to it, But it is still a long slog up the ladder, which is one of the reasons why service lifts are so important. And again, the tower's in sections so that it can be delivered around the country without demolishing villages. Sometimes, if we're running a long distance and we haven't got room for a proper platform, we can put a half moon in place. No fall protection on the platform, but we assume you will keep your lanyards connected at this point because it's quite a long way down. The cable again breaks free from its mounting and hangs in the centre of the tower for the last 10-20 metres or so that it can rotate as the nacelle yaws into the wind. And the lift eventually runs out of space. Remember, the tower is getting narrower and narrower as we get to the top. So the lift tends to park itself about half a platform from the top. And we have a normal ladder which then leads to the yaw platform. And then it starts looking very much like the smaller turbine did. We have a yaw ring bolted to the underside of the nacelle, joining it to the top of the tower. A series of disc brakes run around that yaw ring to lock it in position when the wind isn't changing direction. And when it is, we have a series of either electric or hydraulic motors that rotate the entire mechanism around on the top of the tower. The layout of a multi-megawatt nacelle is again more variable than for a smaller version. We always have to have a generator, but we may not have to have a transformer. In a few cases, such as the famous Enercon egg-shaped nacelle, we don't even need a gearbox. They're direct drive with just a shaft linking to a motor and then lots of extremely complicated electronics to condition that power for connection to the grid. But in most cases, we need the same as we needed in the small turbine: gearbox, generator, possibly a transformer, all in a fiberglass box. And in our example, we're looking at a typical design used by a number of manufacturers where we have a nacelle that's 3 metres high, 2.5 metres wide, 7 or 8 metres long. It's a fiberglass box about the size of a sight hut. As before, we have our wind sensors on the roof as far away as possible from the dirty air cast off by the blades as they spin round. This design is just a fiberglass box with a flat roof. We access the roof through a couple of skylights. Some designs are like before, big cylinder with 2 opening doors. Some have an entire roof section which opens rather like an old camper van. If we take the skin off the box, inside we have the same kind of components we had before. They're just bigger, and there's a little bit more room, so they're laid out a bit differently. The only additional component up here is those 3 green cylinders at the back. That's our high voltage transformer, which used to be at the base of the tower. Now we've removed a lot of the control systems and the hydraulic systems that would just clutter up the pretty picture. We've added in a blow scale, but most of the big components are still here. If we look at the very front of the nacelle, we have a couple of bearings which support the main shaft, which is a hollow tube, 50, 60, 70 centimetres in diameter. It's hollow so that we can get electrical cables in through this main shaft into the hub to drive all the control systems inside the hub. And we have a couple of pins on the first bearing that lock the main rotor in position if we need to access the hub. It's a safety feature. If you're in there and it starts rotating, it gets scary. So our main shaft drives our gearbox, which is mounted centrally because it's often the heaviest component. Out of the back comes a high-speed shaft, as before. That's where the braking system is. High-speed shaft then drives the generator, which is usually oil-filled. The generator then supplies 690 volts, in this case into our transformer, which is sitting right next to it. That high-voltage signal then passes through the switchgear and the cabinet, down the dropper cable, straight down to the bottom of the tower, through those switches on platform 2 and off to the substation. And that, as an overview, is pretty much all there is to it. The only thing left to talk about are the blades, obviously, to actually do the work. We still have 3 of them. They still pitch, in other words, they twist on themselves to line up with the wind. And you access the hub through the gap between this fiberglass cowl and the cast hub. It's a bit of a wriggle. You wriggle through, usually feet first, crawl through the hole in the middle of the hub, and inside the hub you'll find the control electronics, the pumps, the motors, the batteries to control the pitch of each blade, rotating it on its own bearing to set the optimum angle for the wind. If we turn the blades through 90 degrees so they edge onto the wind, there's no net turning force. It's a process called feathering, and the turbine will stop. Obviously there is a vast amount more going on inside a turbine, lots of wiring and control systems, lights and sensors, fire extinguishers, etc. But that is basically it, the general overview of most turbines that you find on wind farms today. Designs for the future will be significantly different, but at the moment, it's a windmill on a stick.
Okay, questions? Straightforward? rotates. All these blades, just like a helicopter, can get aligned. Now, how do we make those? How do we make those blades? And as we discussed yesterday, let me show you how those blades get manufactured, because they are made with composites. So So very simplified way, but what do you think is the most important component on a blade? What do you think is the most, in a blade, what do you think is the most important component from a structural perspective? Think about the wing of an airplane. So if you think about the wing of an airplane, the skin of the wing is very thin. In fact, if you go to a museum of aviation, and you look at the first aircraft, people were using clothing or like a silk or even paper for the wings. So the wings, the skin of the wings is very thin. And the same is true here. You know, the skin of the wings doesn't have to be very thick. It just has to be strong enough to support the pressure of the wind. So in an airplane wing, probably the most important component, there's an I-beam that goes right through the middle. Okay, so if you were to cut look at an airplane wing, and we saw a little bit of that in the Boeing video of the 787. What you have is going to be an I-beam. Okay? And then around the so that's what the wing of an airplane looks like. You have an I-beam, okay? This is the most important component. So if you think of the wings of an airplane, you have a lot of these. So this I-beam has to be very stiff. The bending stiffness of this has to be very high. You don't want the wing to be doing this, okay? So that stiffness is controlled by, number one, this separation. It actually goes with the second power on the separation, and then on the stiffness of these pieces. These pieces have to be very stiff. So if you are a Boeing engineer and you are designing this component, you want your carbon fibers to be running this way, okay? This is going to give you a lot of bending and stiffness. Now, our colleague said, well, be careful because, you know, what if there is some torsion here? Well, so we got to take care of torsion. So we're going to put fibers at plus or minus 45 degrees, so that takes care of torsion. Your bending stiffness is given by the fibers here. Your fibers here. You got to take care of shear stresses in the web. And that's the main component in your wing. Okay? Same thing on the blade. You need a very stiff member that's going to carry the whole structure. And then all you need on the surface is a skin, and the skin has to support the pressure applied by the air. So you can do that calculation. You know the air speed. You know how much pressure the air is going to be applying to the blade, and then you can do that calculation. So when you make going back to the video. What you have is you have a mold and rider. So those are your fibers. You see how the fibers are being applied. Takes care of the skin. And in this case, these fibers are really what controls the stiffness of that member. Okay, you don't want the blade to be doing this, so you need the stiffness, and that's what the fibers give you. And obviously, glass fibers are being used for most of these structures. The next step is really there is your main member there. And that member in the center is what gives you the bending stiffness. If we could make this out of carbon fibers, it's going to be a game changer, because now, because of the stiffness of the carbon fibers, you can have longer members, having the necessary rigidity to withstand all the forces that you have. And by the way, the forces here are tremendous. If you start looking at the speed of the tips of these blades, I mean, in some cases you reach almost supersonic velocities. I mean, this is hard to believe. But when you have a 150-meter diameter blade spinning fast, if you look at the speed at the tip of the blades, I mean, we're talking serious business here. I mean, the stresses that you get in these structures are just astronomical. And this is why you have to have special materials to build them. You cannot build them out of steel or aluminum. Because they don't have the stiffness. And here's where the density of these materials come into the picture. You know, if you build a large structure, then you have to worry about the weight of the structure itself. These materials are so light, and they are so stiff, that now you can really build fairly large structures without having to worry about that. Let me see. I have one more here. This is a test. These tests are actually so it's a typical fatigue test for this. And when they fail, I mean, the amount of energy that you have in these systems is just so intense that when they fail, I mean, these things explode. And there is if you have time, go to YouTube. There are some videos where actual blades have exploded during operation. I mean, it's just, these are catastrophic events. There's so much energy in these systems when they are operating that when they fail, they really disintegrate. And this is why we have to pay attention to things like strength. We design materials based on linear elasticity, but a lot of times we have to worry about failure. And when we started the discussion this morning with Weibull modules and strength, it's not that we are designing for strength. Most of the times we design for stiffness, and we design for things to operate in the linear regime. But if we are in a gas turbine, or if we are in a blade near a population center, we also have to be concerned about failure. And if they fail, we got to make sure that they fail in a gracious mode, okay? And this is where all this behavior with the fibers come into the picture. I have more information, maybe kind of repetitive. I have actually a good presentation. This is a company that makes, I'm not going to go through it because there's a lot of information, but it's a company that has commercialized blades, and it takes you, and I'm going to make all these transparencies available. They talk about the whole manufacturing process. Then you have to worry about the non-destructive evaluation. you cannot afford to have defects in this structure. So people are looking at ultrasonics, laser-based inspection. X-ray tomography is very expensive, but when necessary, you can use X-rays to inspect the section, make sure that you don't have delaminations or large defects. And then you have to demonstrate that these things can take the stresses and the strains. So if you are the engineer sitting on your workstation and you want to have the formations and the strains, from the curvature of this, you can calculate the strain. You go to your classical laminate theory and you can calculate your stresses, and then you can determine whether or not the material can take that level of curvature during operation. A lot of times these are static tests, but in reality these structures have dynamic loadings, so you have to look at accelerations. I mean, it's a very complicated analysis. Fortunately, we have the tools. In engineering, we have all the tools necessary to look at both the static and dynamic analysis. We have all the material science available. All we have to do is just run the analysis. So let's just stop there. Any questions? I apologize. I have dumped a lot of information on you. I know this is a lot of information to. There are actually entire courses on composite materials. You can go through a whole semester. And when I took that course in graduate school almost 20-some years ago, our final project was to design an airplane. And we were building a glider. This was a one-person glider. It doesn't have an engine. It takes off and it just glides, and then it can land. And we had to design the wings. That was part of my project. So we had to design the I-beam that goes in the wing to make sure that the glider will operate. And then another team had to do the fabrication, and another team had to do the inspection. Actually, the glider flew, and it was actually a very good project. You really get to appreciate all the various elements. It's not just materials. I mean, it's where structures come into the picture. To really understand dynamic states of stress, these are very complicated. You appreciate safety every time a passenger goes up in the air. You have to be very careful. You understand about margins of safety. There has to be a significant margin of safety every time you have people's lives involved in this. So it was a good experience. Believe me, I mean, this I'm giving you in 2 hours what usually takes 6 months to cover. But I hope you'll appreciate it. Composites are here to stay. We talk about the structural applications today, but for composites, a lot of you are involved with functional materials. We have done some work making magnets using this composite principle. Just to give you an idea, we have a very recent project, and on Thursday we're going to talk about critical materials. But a few years ago, China started restricting the export of rare earth elements. So if you look at the periodic table, there's a group called the lanthanides, and these materials are very important. You have europium. Europium is used for fluorescent lamps. You have neodymium that is used for magnets. You have yttrium that is used for solid oxide fuel cells. I mean, there are lots of materials that fall in this category of lanthanides, and then the Chinese decided to start controlling the export of those materials. So the Japanese reacted right away because companies like Hitachi, Sony, all the electronic companies, even the South Koreans, LG, they went into a panic mode because without access to these rare elements, you don't have electronics. And if you open your laptop or your iPhone or your plasma display at home, there are so many rare elements that you will not believe it. Same thing in military aircraft. The US went into panic mode because there are lots of magnets. I mean, there are like 75 magnets in an airplane. In an automobile, there are about 25 different magnets. And all of these magnets contain rare earth elements. In particular, neodymium, this is one of the most widely used magnets. So we had a crash program in the US, and I'm going to talk about that on Thursday, to identify replacement for these rare earth elements. And we came up with a magnet that contains iron and nitrogen. There's a phase called Fe16N2, iron nitride. And that material has the highest saturation magnetization value ever reported. It has very low coercivity, and it's also unstable. If you heat it above 175 degrees, it loses all its magnetic properties. So the challenge was to make magnets without heating them above 175 degrees. So you cannot do any sintering, for example. And the approach that we pursued was to make bonded magnets. So we made a composite where we took nanoparticles of this phase, Fe16 and 2, and we embedded these nanoparticles in a polymeric matrix. And the nice thing about it is that we could make objects with complex shape. I want to show you something that we did with additive manufacturing. We made a three-dimensional magnet by printing the magnet using this bonded approach. And doesn't contain any rare earth elements. And to predict the properties, we use some of these rule of mixtures approaches that I just described today. It was not an application focused on structural behavior, but we had to make sure that these magnets that we were making could resist all the stresses, vibrations that you will see in an automobile or an airplane, okay? So composites, again, structural applications is the main interest, but for functional applications, we also have, and I want to show you an example on Thursday when we talk about thermoelectrics. We have made composite thermoelectrics, and we are using the very same principles, looking at the interfaces. There things get complicated because, as you will see on Thursday, heat gets propagated in materials to vibrations. The interfaces can be bad for that, so we'll talk about that. Again, sorry for giving you a lot of information, but I hope you will appreciate. You know, this is important. We are making airplanes. We are making windmills. We are going to be making automobiles with composites. I mean, this is real, and these are big economies. We are looking at carbon fibers with lower cost, so we can introduce them into the broader markets. The higher the volume, then the price goes down. So once these materials get into the auto industry, you're going to see composites everywhere. Okay? Any questions, comments?
Yeah, you told us the future of mechanical technology will probably rely on composite technology. Sure. Can you tell us a little bit about reuse, possibility of reuse, recycling of this material, or reprocessing, or the treatment of waste during processing?
You know, this is a great question. There is, in the US, slowly is catching up, and it's called sustainability. And there's something called life cycle analysis. So it's something called cradle to grave, de la cuna a la tumba. And that is one of the most important things. So when you look at metals, if you talk to a company like Alcoa, where they process aluminum, you know, they love to sell aluminum to aircraft industry because, you know, they melt cans from soda. They melt aluminum from everywhere, and they can reprocess it, and they can sell it back again. You cannot do that with composites. So this is one of the biggest problems that we have. Now, carbon fibers are so expensive that there was a small company that came to work with us at the lab, and they were purchasing all the waste from the 787. So every time you make one of these large composites, I'm not sure if you remember in the video, they were making these structures, and then there was a machine cutting pieces. So there was a lot of scrap from composites. They were melting the matrix. They were removing the matrix to recover the fibers and then reusing the fibers. Now, when you do that, you pay a penalty in properties. But you can resell these fibers, and they still have very good properties for automotive applications, for example. So they were trying to break into the automotive market by recovering the fibers from the scrap composites that the aerospace industry wasn't using, removing the matrix, and then selling those fibers as chopped fibers for automotive. And they were getting there. I mean, they were paying a penalty. We actually measured the properties in the laboratory, tensile strength, Weibull modulus, everything that we talked about this morning. And they were not as good as the as-received or as the as-processed fibers, but they were still very competitive. But that is probably one of the biggest problems with composites. It's very difficult to recycle. It's very difficult. Even if you wanted to recover the fibers, you know, you introduce so much damage when you remove the matrix. So this is a problem, okay? So when you do your cradle to grave analysis, there's going to be a penalty that you pay with this material. That's actually a great question. So from a sustainability point of view, nothing beats metals. You know, metals are great. There is a plant of Alcoa very close to where we live, and you know, they recycle aluminum, and they melt the soda cans, and it goes back, and they send it back to Boeing. You know, most aircraft, except for the 787, are made out of aluminum. So it's one of the biggest markets for aluminum. So being able to melt and recycle is a great part of the business. You cannot do that with composites. That's a good question. That's a serious problem. So yeah, And that has to go into the equation. It's, there is no secondary market for a lot of these composites. So. And that has to be a factor into the cost. We have talked about how important the economic angle is for these systems, and that is a factor that goes into the calculation. That's a good question. What else? Yeah, with nanotechnology, we are having some serious issues in the U.S. I don't know if you have heard about asbestos. We used to use asbestos for everything, insulation, floors, ceilings. And nowadays, it's a big issue, asbestos. I mean, nobody wants to touch asbestos because of the litigation. People have taken companies to court. Companies have gone bankrupt because of asbestos. So now with nanotechnology, people are very afraid of nanotechnology. So in the case of our magnets, yeah, that was, we were talking about 10, 20 nanometer particle sizes. These are very small, and these fall in the dangerous category. So we had to make sure that, in fact, when we do mechanical testing, we have to do first some sampling to make sure that when we break these composites, nanoparticles are not going to come off flying. And as a result of the processing with these polymeric matrices, most of these nanoparticles get encapsulated with a thin film of polymer, and they agglomerate. So that doesn't become an issue, at least with polymer matrix composites, because the bonding is very strong. You have very strong bonding. But that can certainly be an issue. And believe me, people are very afraid of nanotechnology. I mean, the fact that things can go into the lungs, that's a big issue. And the national academies in the US has paid a lot of attention to that. There's an organization called OSHA, the Occupational Safety and Health Administration in the US. They pay a lot of attention. Every company that works with nanotechnologies, they have to install some safety mechanisms to prevent the workers from being exposed to nanoparticles. So, good question. I mean, that's a big issue. And that adds cost to nanoparticles, because if the industry has to pay for a special features for safety and health, that just becomes more expensive. And then the fear of the public that if something breaks, that you'll be exposed to. So that's a big issue with carbon nanotubes. It's a big issue with small nanoparticle size. So. Okay? Okay, very good. Well, thank you much, and we'll see you tomorrow. Okay? Thanks.